Let's work on example 13.13, finding the absolute extrema of a function on a bounded domain. So we need to find points either in the interior of our domain that give us zero partial derivatives or a partial derivative that doesn't exist, or we also need to check our boundary because our partial derivatives don't exist on our boundary either. So let's translate the following information onto a separate sheet. I have a function from R2 to R given to me by f. And I'm going to define this function over a triangular region in the plane bounded by the lines x is equal to 0, y is equal to 0, and y is equal to 9 minus x. Okay. So let's copy down what we know. The function that we wish to minimize and maximize. 2 plus 2x plus 4y minus x squared minus y squared. And we're concerned with this function on this triangular domain, where this is the line y is equal to 0, this is the line x is equal to 0, and that is the line y is equal to 9 minus x, meaning that this point right here is 9, 0, and this point right here is 0, 9. Okay, so let's look at interior points first. This function is a nice smooth function. Its partial derivatives are going to be nice and smooth everywhere. They're going to exist everywhere. We just need to figure out when the partials are going to be 0. So we've got 2 minus 2x has to be 0 for the partial derivative in the x direction. That puts me at x being positive 1. And if my partial derivative in the y direction is also 0, that gives me 0 is equal to 4 minus 2y, or y is equal to 2. So the only interior point is when x is equal to 1 and the y value is equal to 2. So let's evaluate the function as we go. Right, this is one potential location for the absolute extrema. And the function value here is a 7. Okay. Now that's the only interior point, but now we need to check these boundaries. So let's start with this one. On our y-axis, or when x is equal to 0. So on x is equal to 0, our function values, oops, not the y value is 0, but the x value is 0. So it's going to be just a function of y, and it's going to be 2 plus 4y minus y squared. Right, that's this function value, but I'm looking at the slice on my y-axis. Okay, so let's set this equal to, or first we need to find a derivative. So this is just a derivative of a single variable function, but I'm still going to denote it f sub y because it's the derivative in the y direction, right? There's no x's here. This is going to be 4 minus 2y. It's actually the same thing. Of course, it's the same function. Of course, it has the same partial derivatives. This is going to be 0 when y is equal to 2. So if you think about this, we are looking at a slice of this function, right? This function is like a surface coming out at you. So this function value f has a one-dimensional function on that slice on the y-axis, and the extrema can occur at interior points of this domain when the derivative is 0 or does not exist. This partial derivative is always going to exist, so we set it equal to 0. I could have a local maximum there, which means that I need to check the point 0, 2. Right? I need to look at this point right here when x is equal to 0 and y is equal to 2, because there's a hilltop there, or a valley. We don't know which one yet. Okay, but also for the same reasons, I have to check, oops, I should not have done that. There we go. I also have to check the endpoints of this interval, right? Because my derivative, or my function, can obtain extrema at endpoints or at interior points. So I need to also look at 0, 0, and 0, 9. I did not like that 0. There we go. So if you evaluate your function here at 0, 2, you find that it's equal to 6. 0, 0, you find it's equal to 2. And 0, 9, it's equal to minus 43. All right. These are also potential contenders for local extrema or global extrema. Now let's look at our other boundary when y is equal to 0. So when y is equal to 0, our function is going to be a function of x. So go here, look at when y is equal to 0, and you find that their function has a value equal to 2 plus 2x minus x squared. So this function can have extrema at interior points when the derivative is 0 or does not exist. It's always going to exist. So when are we going to get a 0 derivative? Of course, it's the same thing because it's the same function. Okay, so when x is equal to 1, this means that we need to look at interior point when x is 1 and y is 0. But we also need to look at the boundary points of this boundary. It's kind of weird. We need to look at the boundary points of the boundary. So the origin and 9, 0. Now we already have the function value at the origin. We got a 2 there. And if you evaluate your function at 1, 0, you get 3. And your function at 9, 0, you get minus 61. Okay. On the last boundary. So the line y is equal to 9 minus x. On this line, our function value, let's just write it as a function of x. So I'll replace my y values. We get 2 plus 2x plus 36 minus 4x minus x squared minus 81 minus 18x minus x squared. All right, let's clean that up. This is minus 43 minus 2x squared plus 16x. All right, this function can have extrema when its derivative is 0, which is going to tell us that minus 4x plus 16 is equal to 0, or x is equal to 4, or at the boundary. So let's look at the interior point of that boundary. When x was 4, what's the y value? 9 minus 4 gives us 5. And then the boundary points of this boundary, I think we've already checked them, 9, 0, and 0, 9. But just for completeness, let's write it down. Okay, your function value at 4, 5 is going to give you minus 11. 0, 9, we found to be minus 43. And 9, 0, minus 61. Cool, so we're pretty much done. If these are the only possible places where extrema can happen, I just need to look among them and figure out which one's the biggest, which one's the smallest. So it looks like we have a absolute minimum at 0, 9. Right, we found that a couple different places. Oh, wait, I have 0, 9 giving me 2 different values. Oh, silly, okay. Yeah, you probably are thinking, hey, slow down. This was 4, 5, 9, 0, or actually, no, 0, 9. Yeah, that's what I wanted. Where's 0, 9? Minus 43. I just wrote down the wrong number. And then the 9, 0 is the minus 61. Okay. Okay, almost said something wrong there. Our absolute minimum occurs at 9, 0 with a minimum value of minus 61. And our maximum, what's our maximum value? I think it was up at the very beginning at 1, 2, giving us a max value of 7.